This lesson is a quick review of probability so that we can do some more complex things in future lessons. Quick review: probability is a measure of how likely an event or an outcome is to happen. We have two types of probability. There's experimental probability, where we actually do the experiment. For example, flip a coin 100 times, see how many times it lands heads. If it lands 40 times, the probability experimentally would be 40 on 100 of getting a head. Or the theoretical probability, which in most cases we'll calculate, in which we just consider what would possibly happen. So the example with the head, let's say there's two sides, heads and tails. Probability of getting a head is 1 on 2. To calculate probabilities, we'll find the probability of some event occurring being the number of ways the event can occur divided by the total number of outcomes in the sample space. The other two formulae that are here, the expected frequency. So if I flip a coin 1,000 times, how many times do I expect to get heads? Well, I'll multiply the relative frequency, so the probability, times 1,000, the number of times I flip the coin. Complementary events. The event A dash being the event A not happening. We know the probability of an event happening plus the probability of it not happening needs to equal 1. The event can either happen or it can't. There's no in between. And this will be useful to solve some bigger problems in the future. Let's go on with an example, looking at how we can solve one of these problems. Use a grid to determine the probability of obtaining 6 or better when adding together the uppermost faces when 2 tetrahedral or 4-sided dice are thrown. So I'm using a grid. My dice have 4 sides each. I'll make one part of the grid the first die, and second part of the grid, or the vertical part of the grid, the second die. I'll list down the possible outcomes of both of these die. So the first die could be 1, 2, 3, or 4, and the second die could be the same. From here, I'm going to form a grid in which I'm going to look at the outcomes of all of these possible dice rolls. It says adding together the uppermost faces. So I'm going to be adding these together, and in each cell I'll add the outcome. So in here I have 1 on the first die and 1 on the second die, which means add them together for an outcome of 2. I can go ahead and fill in the whole table, all the possible outcomes, so essentially the sample space. I'm trying to calculate the probability of obtaining a 6 or better. That's my event. So I need to look at the number of times the event occurs. 6 or better, there's 1, 2, 3, 4, 5, 6 occurrences of a 6 or better. And then divide it by the number of elements in my sample space. It's a 4x4 grid, meaning there's 16 total elements in my sample space. I can simplify this fraction to 3 on 8, and if I want, I can put it as a decimal or as a percentage. Either of these representations are fine. Probably decimal and fraction are more common. That's using a grid. You can also use tree diagrams to simulate some of these scenarios, especially when we have more than 2 events occurring. In this scenario, we're tossing a coin 3 times, and we want to find the probability of getting exactly 2 heads. I can't use a grid for this because I can't have the first coin, the second coin in my table, and then expect somehow to be able to put the third coin in there in 3 dimensions coming out of the page. It just won't happen. The tree diagram is going to be the most productive in this case. From a starting point, I'm going to look at the first toss of the coin. My outcome can either be a head or a tail. Similarly, for the second toss, or the second coin, it could be a head or a tail from both of these. I can do the same thing for the third toss. I can list my sample space. The very top row, where I get a head in the first toss, head in the second toss, head in the third toss, will be represented as HHH, showing 3 heads. And I'll do the same for each of these branches on the tree diagram. Because I know it's equally likely to choose a head or a tail, I don't need to mark the probabilities on this tree diagram, but in the future I will have to. Now that I've got my tree diagram complete, I can calculate my probability of getting 2 heads. Again, what I'm going to do is look through the sample space for outcomes where there's 2 heads. There's 1, there's 2, there's 3. And then divide it by the number of elements in the sample space. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 in the sample space. So the probability of obtaining exactly 2 heads would be 3 on 8. You can use a similar idea of tree diagrams for more interesting scenarios, maybe more life-related ones. For example, 2 cards are dealt from a well-shuffled pack of 52 cards. What's the probability of obtaining 2 aces, or at least 1 ace? I'll start with the tree diagram again, and I'll look at what's happening to the first card and to the second card. And then I'll have my sample space. This will let me plan my tree diagram a little bit better. So the first card can either be an ace or not an ace. So I'd normally define that somewhere here. So let A be ace, let N be not ace, just so I don't get lost in my diagram. Now the thing to be careful here, getting an ace or not getting an ace is different to flipping a coin heads and tails. There's 52 cards in the deck, and there's only 4 aces. So the probability of getting an ace is 4 on 52, and probability of not getting an ace is 48 on 52. So I need to be careful about that. The second card can also be an ace or not an ace. And when I'm writing the probabilities on this second set of branches, I need to be careful because I've already removed 1 card. So I actually only have 51 cards remaining in all of these scenarios. And I need to think what's happening. So in the top 2, these 2, I've removed an ace. So I've only got 3 aces remaining, but there's still 48 cards that aren't aces. I need to always make sure that when we branch out in a tree diagram, they add to 1. Similarly, in the bottom half, I didn't take out an ace, so there's still 4 aces remaining. We took out a different card, so 47 on 51. My sample space, I've got 2 aces, an ace and something else and an ace, and 2 other cards. Here I can calculate the probability of all the outcomes in my sample space. So the probability of getting both aces, I'll use the multiplication principle, which means if I want an ace and then an ace, I need to multiply the probabilities. The probability of getting the first ace was 4 on 52. Probability of getting the second ace was 3 on 51. I end up with 1 on 221 as my probability of getting 2 aces. And you can see this as just multiplying by these 2 probabilities as we go along the tree diagram to get to that outcome. So we can do the same thing for the other 3 outcomes, and we can see the probability of all these outcomes occurring. As a check, add all these together, make sure we get 1. So I can answer part A of my question now. What's the probability of getting both aces? I can just read that off my diagram and see that it's 1 in 221. Which means if you're playing Texas Hold'em poker, you'll have to wait 221 hands to get the pocket aces. Part B is a bit more interesting, at least 1 ace. So probability of at least 1 ace. We can calculate this 2 different ways. I could calculate it by saying, well, these 3 scenarios all have at least 1 ace, so I can add them together. Okay, or alternatively, I can say the probability of at least 1 ace is all of the probabilities minus the case where there's no aces. Okay, which is probably a lot easier to do than multiplying and adding all of these together. So this last one was using the complementary probability idea. Here's some questions to have a go at. They are over the page, and there's a few interesting ones in here. Things about archery and things about passing exams and things with solutions at the bottom.